Okay, hello everybody. Welcome to this talk from Auckland Structural Group. This evening we have the pleasure to have Professor Massimo Fraggiacomo from University in Italy. He's the Director of Centre of Education and Research in Earthquake Engineering. Massimo has led a number of the revisions in Eurocode 8, internationally recognised as a timber expert, particularly in timber concrete composites and seismic engineering, and has also actually spent time here in New Zealand about 20 years ago at the University of Canterbury. So we have a very exciting talk to look forward to, and we leave Massimo the floor.
Yeah. Okay, so thank you, Gary. So good afternoon, actually good evening, I would say, everyone. And very pleasing for me to be here after a few years. I was in Christchurch between 2005 and 2028. And then I returned for some years until 2012. But from 2012, that's the first time I'm back here in New Zealand. I'm very pleased to be here. So today, I'm going to share with you some basically facts about the revision of the Eurocode 8 in terms of seismic performance of timber structure. I will start with a short introduction, introducing quickly the history and the different parts of the Eurocodes. Then I will going to talk about some modifications, in particular talking about timber structures in Eurocode 5 and 8. 5 we'll see is a timber design, and 8 is seismic design. And then I'm going to give some very basics of seismic resistance on timber structure according to the Eurocode, and then to discuss with you some of the main updates of the timber chapter of the Eurocode 8. So we will go through the revised definition of structural types, new safety format for the seismic design at significant damage. Then we will go through the new definition of the behavior factor according to the Eurocode 8, some ductility rules for dissipative zone, capacity design overstrength factors, and then I will conclude by giving you just a link where you can download a worked example of seismic design of a multi-story CLT building, which unfortunately is in Italian, because the founding agency was the Italian Department for Civil Protection, and they said this, we funded you, and this must be used by the Italian engineer. I said, but the Italian engineer, they know some English. They say, no, they don't know English, so you have to do it in Italian. But hopefully in the future, we are going to translate it also to English. So first, history about the Eurocodes. So 1975 is the year when the European Union, or let's say at the time was not the European Union, but European country decided that if they wanted really to build a new Europe, they should have made trade possible among all the countries. And they identify as a major way to avoid any trade barrier to have a common design code. Design, we are talking about, of course, civil engineering. So in 1975, this idea, then you see it took more or less 30 years to get the first generation of the Eurocode ready to be used in design. Now, in 30 years' time, many things changed. You can understand, in 30 years, if you look back, what was 30 years ago, completely different. We didn't have artificial intelligence, so we didn't have the mobile. So in 30 years, really many things changed. So for this reason, you see, in 2010, we said, okay, we need, now that we are ready with the first generation, we need to start with the new generation, the second generation, in order to implement what was all these changes occur in the first 30 years. So it took some other year, as you can see. 2015, we started this value of revision. So we had some what we call project teams, a group of groups of six people, usually 2 academics, 2 people coming from the industry, and 2 people coming from the design office, meeting together and trying to write, the new version of all the Eurocodes. This was a long process, as you can see. And this process is still ongoing. So we had, because after we write a first draft, then this draft must go through a process of voting. So all the 28, 29 countries must say, yes, we are okay with this new revision, or no, we are not, or yes, we are okay, but we want you to change this, this, and this. So this process took quite a lot of years. So now we are here, 2025, so we still have to have the vote, the final vote on the new version of the Eurocode 8. Hopefully it will go well. If this goes well, as you can see, 2028, in 2 years' time, 3 years' time, this will be the latest date of the withdrawal of the first generation of the Eurocode. So the new generation will be in force from 2028. So look at this timeline, as you can see, from 2010 to 2028, 18 years to get a new code, which is quite a lot, I would say. Hopefully in Australia and New Zealand we will be faster than 18 years. But the problem is that since in Europe we have, 26, we don't have really a United States of Europe, as you can understand. We have 28 different countries with different governments. So all the process is very long. But hopefully in 2028 we will have the new version of the European code. So the Eurocodes are many documents. So you can see here we go from the Eurocode 0, basis of structural design, which means basically limit state design, serviceability, mistake, etc., through the Eurocode 8, design of aluminium structure. All of them is not only one, except the EN 1990 is one part. All of them are more parts. I just wanted to highlight EN 1993, Eurocode 3, design of steel structures. We have 20 parts. So 20 parts of Eurocode if you had to design a steel structure, which is some way a bit strange because in my mind, when I was a student, also as a researcher, I would have thought that designing a steel structure is fairly simple. Instead, there were 20 parts, to go all the kind of design, the member, the joints, the silos, tanks, and so on. So altogether, we have something like probably 40 parts, all the Eurocodes together. Now, some of those parts are material dependent. So you can see here, EN 1992, reinforced concrete, steel concrete, composite, timber design, EN 1995, 1996, masonry, 1999 is aluminium. Then we have some general horizontal parts, EN 1990, EN 1991, action structure, everything but earthquake, and then earthquake comes in EN 1998, seismic design, and of course EN 1997, geotechnical design. Now, if we want to design a timber structure according to the Eurocode, basically you need to use Eurocode 0, basic of structural design, Eurocode 1, action of structure, everything but earthquake, then the Eurocode 5, which is the normal static design of a timber structure, and then the Eurocode 8, which contains some additional provision for the design of timber structure for seismic, action. So, in the current version of Eurocode 8, the timber part was only 6 pages. So if you compare the current version of Eurocode 8, timber, 6 pages, reinforced concrete, 40 pages, steel, 40 pages, masonry, 30 pages. So timber was just a fraction. And of course, we decided that it was time to give more provisions to the designer, because otherwise, of course, there were just some general concepts, but we were missing at that time, in the older part of the Eurocode, we were missing, for example, all the capacity-based design principle, all the overstrength factors. So in the new Eurocode 8, there will be basically a chapter dealing with timber design of 14 pages plus 6 pages of annex. So now, in this new Eurocode, we will have a similar kind of, let's say, weight in terms of pages for timber, concrete, masonry, and so on. And this is very good news. Another important thing, there is also one part of the Eurocode 8 dealing with assessment and retrofitting of buildings, which is very important when you are in an old country like Italy or Europe in general. So in this part here, currently there is no information on the designing of timber building, on how to retrofit a timber building. In the new part, so there has been a revision also of this part. They also here has been added, as you can see, one chapter, 26 pages plus 3 pages for the design of, for the retrofit of an existing building in earthquake-prone area, which is quite an important thing. There will be also one part of the Eurocode 8 dealing with bridges. So if you want to build a bridge, you have a general part, on bridges in the timber chapter in the Eurocode 5. But then you have also one part of the Eurocode 8 dealing with the seismic design of a bridge. Currently, no information. In the new one, there will be an annex with 5 pages. Not many, but much better than nothing. Okay, so I will skip this because it's not so important. It's just a testing about how, a design standard on how to test cyclically a timber structure. And I will move instead to the current version of Eurocode 5. Eurocode 5, we said before, is what we need if we want to design a timber structure, a basic timber structure under seismic action. So there are 3 parts. 1995-1-1, general rules and rules for buildings, structural fire design, and bridges. All those 3 parts have been completely revised, and there will be 2 new standards, one about execution, lots of discussion about execution, because when it comes to execute, to build a timber building, there are some things that we need to check, moisture content, etc. So there will be a standard about this, and then another standard about the structural design of timber concrete composite structure. Timber concrete composite structures be used more now, particularly in Central Europe. The idea is basically what is a timber concrete composite structure? It's like a steel concrete composite, except that we replace the steel beam with a timber beam, connect in some way with the concrete. So some basic or seismic resistant timber structure, something that you all know, but just to introduce some definition according to the Eurocode 8. So we will basically classify a timber design for earthquake action as a low dissipative structural behavior or dissipative structural behavior. So low dissipative means basically that we, in some way, design elastically our building, and we just consider a small value of the behavior factor Q. The behavior factor Q is what in the New Zealand standard is called K mu. So it's basically the value that we divide our elastic spectrum for in order to get our seismic action into account. Dissipative structural behavior instead means that we are designing a dissipative structure so that we want to get some energy dissipation. And in this case, we can get a higher value of the Q factor, in general, more than 1.5. So in Europe now, for low dissipative structural behavior, the behavior factor is 1.5. Instead, for dissipative structural behavior, the behavior factor would be greater than 1.5. So just to recap a little bit, if you have to design a small building like this, of course, for seismic action, what we need to take into account is what we call Europe seismic weight, which is the permanent action plus 1 fraction of the imposed action. So if there is a snow, for example, if we are on the in a non-snow area, psi 2 would be 0. If we are instead in a high 1,000 meters, this psi 2 could be 0.2, 0.3. So seismic weight, this one is multiplied by W, is basically is divided by G, which is the gravity acceleration. So W over G is the mass of our roof. This is multiplied by a coefficient lambda, then is eventually multiplied by SR. SR is the ordinate of the reduced spectrum. So we have what we call the elastic spectrum that depends on the seismicity of our zone, where basically we have the acceleration versus the proper vibration period. And the Q factor is what I said before, is the K mu, according to the New Zealand standard. It means that we are going to divide the elastic response spectrum by Q. For example, if we have a highly dissipative structure, we have a reduction of the spectrum. Then we enter with the proper vibration period of our structure, and we got eventually SR of T1, which is our, say, horizontal acceleration that we apply to our structure. So one important point of discussion when we wrote this new draft of the Eurocode 8 was that in the old version there was no information on the structural system that we can use in a seismic region. So there was an explicit request from the engineers to place a table like this, where you can basically summarize with the sketch the type of structure, the type of lateral load resisting system, and then we have a kind of summary, short description of the structure that we are talking about. So lateral load resisting system we can use is what we call, for example, the cross-laminated timber structure, which is made of a solid panel, or we can use a frame wall structure. Frame wall structure is what in New Zealand was used to call light frame construction. Now, for some reason, our colleagues from United Kingdom decided to call not anymore light frame construction, but frame wall structure. This is partially, I think, due to the fact in some countries, like in Italy, the frame is not really light. I mean, we're not using 2x4, we rather use 4x8. So maybe this light frame could be a bit confusing. So they decided to call frame wall structure. Then we have a log structures. So when we use basically the logs of the beams horizontally, this is kind of typology which is mostly used in the Alps in Europe. And then we have other systems like a moment-resisting frame structure or brace frame structure or vertical cantilever structure. So the idea is that we have explicitly spelled out the different lateral load resisting systems, and then for each of those lateral load resisting systems, there are some provisions regarding capacity-based design and regarding also the value of the behavior factor to be used. When it comes to the basic safety formula for seismic verification of significant damage, so significant damage is basically the ultimate limit state, we have this relationship here, which in some ways similar to the one in New Zealand, except that in New Zealand use the phi factor, which is the strength reduction factor, which is basically 1 over gamma m. So Europe, instead of using the phi factor, the strength reduction factor, use the partial factor. So we divide our characteristics design strength by a safety factor, gamma m. Now, this relationship is different if we are designing a dissipative zone, like a joint, or if we are designing a non-dissipative zone. If we are designing a dissipative zone, we have basically the characteristic strength of our joint. We divide it by a partial factor, gamma m, which is basically equal to 1 because the seismic action is considered as an accidental design situation, more or less like fire. So we don't use the gamma m 1.3 or 1.4 like for a static design. It means that we are using a phi factor of 1, in other words. Then we have K mod, modification factor, which would be the K1 times K2 times K3, so the different partial factors take into account the influence of the load duration or the influence of the moisture content. And then we have this we introduced this new coefficient Kdag, which is called basically a strength degradation factor or strength reduction factor for cyclic loading. So the idea is that if we design a dissipative connection, this dissipative connection will have to undergo through several cycles of loading and reloading in one direction, in the other direction. And if you do some tests, if you compare, for the same connection, you compare the behavior under monotonic loading with the behavior under cyclic loading, we found out that under cyclic loading there is a degradation. So this degradation should be experimentally measured. So basically it's the difference between the blue curve and the red curve. If no tests are basically carried out, we suggested the value of basically 0.8. So in the end, when we design, let's say, a dissipative connection, we are taking the characteristic strength, we are multiplying this by the K1, K2. According to the Eurocode, seismic is a very fast load, which lasts between 10 seconds and 40 seconds. This K mod is actually equal to 1.1, so we can increase the strength by 10%. We don't reduce the strength by the partial safety factor because this is regarded as an accidental design situation, and we reduce instead by 20% to take into account that we have a cyclic behavior. So this is only for the design of the dissipative part of our structure. The design instead of the non-dissipative part of our structure can be done with a normal design format. So K mod, which K1 times K2 or whatever, times FRK and D times phi factor. And in this case, if we design a structure in DC1, so if we design the whole structure as a, let's say, non-dissipative, so we do an elastic design, in this case, we basically use the gamma m with a value larger than 1. So in other words, when we design a dissipative structure, we take into account that we have a degradation because of the cyclic behavior, but the gamma m are equal to 1. Well, instead, we design a non-dissipative structure in DC1. We do an elastic design. We want to make sure that our structure will be always far away from the plasticization. For this reason, we use a gamma m greater than 1, so 1.3, 1.4, 1.5, which will be basically equivalent to use a phi factor equal to 0.7, 0.8, depending on the material. Now, in terms of behavior factor, there was a request to provide for each structural system the value of the behavior factor, which is used then to reduce the elastic spectrum. Just recall that the Q factor is what we call K mu, according to the New Zealand standard. Also here, we were asked to provide, to split this behavior factor in the products of three factors, so QS, QR, QD, which have some meaning when it comes to perform a nonlinear static analysis. But in the end, for the engineer, what really counts is the final value of Q. So basically, you see here, this is the table, the new Eurocode 8. You can see for each different structural systems of the table that I showed at the beginning, for each of those systems, you have the value of the Q factor for DC1, which means elastic design, non-dissipative or low dissipative, a value of the Q factor for DC2, which basically is a medium dissipative structure, and another value for DC3, which is highly dissipative structure. So basically the idea is that the designer should pick up the structural system that he or she wants to design. Then he or she must decide if we want to do a low dissipative, high dissipative. Once we choose the low, high dissipative class, then we have the behavior factor we can use. But of course, then we need to make sure that the dissipative zone will have a ductility high enough to ensure this value, the attainment of this value of the Q factor. So an important concept we wanted to clarify from the very beginning of Eurocode 8 is that a dissipative structure made of timber has a behavior quite different from a dissipative structure made of reinforced concrete, made of steel. Because when we all study a dissipative behavior of steel or reinforced concrete, we were told that the actual plastic hinge will form in the beam. So if we have something like this, we were told, OK, if we have a reinforced concrete or steel, the plastic hinge will form here in the beam, close to the joint, and everything else, so the column and the joint, should be capacity designed for the strength of the bead itself. Now, for timber, it's completely different, of course. For timber, the dissipative component is the joint, while everything else, the column and the beam, shall be designed for the overstrength of the joint itself. So we spell it out from the very beginning. The joints are the only dissipative component, and instead the beams and the column shall be designed elastically. Now, the important point also we wanted to clarify is that although a joint is 90% of the case made from steel fastener, could be nails, screws, dowel, etc., the fact that the joint is made by steel fastener does not necessarily mean that the joint will behave in a dissipative type of fashion. And so we spell out that basically the energy dissipation in joints and connections should take place by flexural yielding of laterally loaded metal fastener. So meaning that this is the kind of failure mechanism that we want to achieve in a dissipative joint. So we want to achieve, let's say, embedding of wood, but we want definitely to achieve some plasticization of the steel. Because otherwise, as I'm going to show now, otherwise the behavior of the joint may not be sufficiently dissipative. This is because the literature is full of this kind of tests. If you perform, let's say, a cyclic test on a connection where you have the formation of the plastic hinge in the fastener, like it is depicted in this figure, then you can see that you have quite a significant hysteresis loop characterized by a significant area. And this area, in some way, measures the amount of energy which is dissipated by the joint itself. However, if you increase the diameter of the fastener, we can still achieve the same ductility, but as you can see, on the same ductility, the area within the hysteresis loop is much lower. Meaning that in this second case, even for the same ductility, but the dissipated energy is much less. So the conclusion is that, yes, the dissipative zones are the joints, as long as we have flexural yielding of the fastener. Otherwise, the joint even though it may be considered as a ductile, but I cannot consider as a dissipative in terms of seismic design. So this one is basically regarded as a dissipative. This one instead as a non-dissipative. So another option that is becoming more common in modern design is to have instead the plasticization concentrated in energy dissipator. So we can hear more and more also in order to avoid damage. So this is an example many of you may know. This building has been built several years ago now, I think in 2011 or 2012 in Nelson, where basically you have that some walls made of LVL are pre-stressed, and there are some energy dissipators, so those plates with this carved U-shaped metal plates, some energy dissipator where basically the energy dissipation should take place during an earthquake. Now, in this case, the design philosophy is different because in this case, we have to follow not the rules that are specifically for the timber buildings, but we have to follow the rules that are stated in the Eurocode 8 for energy dissipators. In this case, basically, only the energy dissipator here will be designed for the reduced spectrum, and everything else, the wood and the screw instead, will be designed for the overstrength of the energy dissipator. So in this way, we left the door open for the use of this kind of advanced system that are not explicitly mentioned in the Eurocode, because also there, I mean, the Eurocode are supposed to be used, are supposed to cover, let's say, 95% of all the buildings. So we couldn't really put all the different systems inside. We put just the most common one, but we left the door open for systems like this to be included, to be designed according to the Eurocode anyway. Now, in terms of screws, very often we are using inclined screws. The inclined screws, as depicted in this figure here, they are very lovely in some way because they are very strong and they are very stiff. Much stronger and stiffer compared to the screw perpendicular to the shear plane. But on the other hand, we know that the inclined screws, they have much less ductility compared to screws perpendicular to the shear plane. So we wanted to state clearly that inclined screws are OK in this one design. Also in DC2 or in DC3 are OK, but they cannot be considered as dissipative. So the energy dissipation should come out from other zones, either energy dissipator or screws perpendicular to the shear plane. Also here, hold down, connect with inclined nails. It's fine in terms of strength, in terms of stiffness, but also this one cannot be considered as a dissipative. Last but not least, we have a joint between panels with some screws perpendicular to the shear plane. This one may be dissipative or may not be dissipative. It depends on the failure mode. If the failure mode has at least one plastic hinge in the fastener, then this one will be dissipative. However, if there is no plasticization of the fastener, also this one is non-dissipative. So we wanted to state this very clearly because often it happens that maybe a timber structure is designed by some professionals, some engineers who have not attended any timber engineering course. In Italy, we don't have many universities offering timber engineering course. So they are more common in Germany, in Austria, but in Italy, just few universities offer timber engineering course. So we want to state clearly that the design philosophy is slightly different when it comes to timber structure. Now, I said before, we need to achieve this kind of failure mechanism. We don't want this kind of failure mechanism in the dissipative connection. How can we make sure that we have one and not the other? Fortunately, when it comes to timber design, we have the Eurocode 5, and now also in the new Australia-New Zealand the new New Zealand standard, there are some formula that allow the designer to find out not only the capacity of the connection, but also the failure mechanism. What I'm showing now is called European yielding model, has been implemented in the Eurocode 5, even in the old version. It will also be implemented in the new New Zealand standard for timber design. So if we take, let's say, if you store this formula in an Excel spreadsheet, we can get immediately the value of the strength of the connection, but also the failure mode. In fact, if the minimum value of those 6 is the first, then we get, you see, a failure mode characterized by crushing of wood, let's say embedding of wood, and no plasticization of steel. With the second one, we get similar kind of failure mode. With the third one, we have, again, no plasticization in the steel. Only if we get the third, the fourth, and the fifth, we have a plastic hinge formation into the fastener. So now, if our joint should be designed as a dissipative, we cannot have the first, we cannot have the second, we cannot have the third. We can only have those three here. So this one would be, if we have this failure mode here, would be DC2. If we have this one, DC2, this other one here would be DC3. Now, how can we make sure that we have, in our dissipative zone, either the fourth or the fifth or the sixth? Basically, we calculate the minimum of the non-dissipative failure mode. We calculate the minimum of the dissipative failure mode, and then we use, you see this design inequality, we use a kind of safety coefficient 1.2 between the non-dissipative and the dissipative one. Why we introduce the criteria here? Because without this, it may happen, for example, that the lower value is a dissipative one, could be 10 kilonewton, for example, and then you have the lower value of the non-dissipative one is 9.9. Oh, sorry, is 10.1. So the minimum of the dissipative is 10, and the minimum of the non-dissipative is 10.1. So theoretically, we should have a dissipative one, but the difference is so small that considering the scatter of timber, it's very likely that we get actually another one, another failure mode. So to make sure that really only the wanted failure mode will occur, we use this coefficient 1.2 as a kind of, let's say, safety coefficient between the dissipative and the non-dissipative failure mode. Now, another thing we want to avoid, of course, is a brittle failure. And brittle failure may occur just around the connection. So those are all failure modes that may occur in a timber connection. You can see splitting, row shear, block shear, plug shear, net tensile failure. They're all brittle. So we need to make sure that those failure modes will not occur. How? Using capacity design. Capacity design means that when I'm going to basically do the verification, for example, for splitting or for row shear, I'm going to take here the value predicted by the European yielding model, by the formula that we saw before, which is the dissipative one. And I multiply this by the overstrain factor, which could be 1.6 or 1.3. And I'm going to divide this by the strength degradation factor, 0.8. So in the end, 1.6 divided by 0.8 is the number of 2 that I'm sure you have in the New Zealand standard. In the old New Zealand standard, I remember very well, there was this number of 2 that was considered as the overstrain factor. So this means basically that the strength of those brittle failure mode must be twice as much as the strength of the dissipative failure mode that we saw before, in order to avoid, of course, this kind of brittle failure mode. Of course, there is also another way, which is use reinforcement. So this is this can be designed as a ductile connection. You see there are some dowel pins in a corner joint. Unfortunately, when you do a test on this kind of building, often you get this kind of crack here, which is very brittle. So in order to prevent this crack, we can also think about using some reinforcement. So using some screws to basically stitch, or actually to stitch, to prevent this crack from forming. And in the new Eurocode 5, there will be also some rules given on how to design this kind of reinforcement. Now, the overstrain factors, with this value 1.6, 1.3, really depends on the failure modes. So there is this table here showing that if the failure mode is very brittle, then you see the overstrain factor is 1.6. If we have, again, failure mode like this, which is a brittle failure of the hold down, again, 1.6. Again, here, failure for tear out here of the anchor, 1.6. And withdrawal screws, again, 1.6. 1.3, this 1.6 can be reduced to 1.3 if instead you have a connection where your screws, your nails are basically perpendicular to the shear plane. Because in this case, maybe we don't have dissipation, because we have only crushing, but in any case, the behavior, for sure, is not brittle, it's more ductile. So in this table, the designer can find the value of the overstrain factor. Now, as I was telling before, for each structural type, so the frame wall structure, the CLT, the loghouse, etc., there is a chapter in the Eurocode 8 giving some general rules and then giving some capacity design rules for designing DC2 and DC3. Those capacity design rules can be capacity design rules at building and wall level, and also capacity design rules at connection level. So basically, you can see here, now I'm going to speak a little bit more, some connection that were not well designed. Because we are going to see shortly that the dissipative part actually didn't fail, but failed the brittle part. It means that the actual anchor connection was not well designed. So the most important thing, of course, the most important thing was missing the old Eurocode was what are the dissipative zones for different structural systems. So, for example, when it comes to a CLT building, what are the dissipative zones? Now, fortunately, many tests have been performed, some of them on shaking table. So, for example, this test I'm going to show you now is a test that was performed by Professor Ceccotti from the National Research Council of Italy in 2008, 2007 in Japan. And this shows clearly, the shaking table test shows clearly which one was the dissipative failure mode. So I'm going to take away this, just a moment. So if you look at the video, you can see quite clearly some of the wall panel rocking in this way. So basically, the dissipative failure mode of a building like this in CLT is rocking, rigid rocking of the panel. So the panel itself is almost rigid. So all the plasticization must occur in the connection between the panels themselves. So if we have like a wall made by two strips of CLT with this intermediate joint, this would be the dissipative failure mode, which means that what we have to design to plasticize is the screw connection between the two panels and also the nail connection between the angle brackets and the wall and the hold down and the walls. So again, this just to show a bit better what we are talking about. Here in red are the dissipative connections CLT buildings. CLT building can be designed in DC2 with a Q factor of 2.3 or in DC3 with a Q factor of 3.2. The most important difference between these two kinds of design, in DC2 you can see there are just few vertical joints between the panel. In DC3, rather than having one monolithic wall, we have more strips of panels connected with this, let me put again the pointer, connected with these vertical joints here. I would say in Europe, usually, particularly in the Central European country, Germany or Austria, this is the way to construct. So to cut the whole wall, which is as long as the whole building, and to make as few walls as possible to construct the building. In this case, the behavior factor is 2.3, so the K mu would be 2.3. So again, in blue now, those are the dissipative joints. So the joints that we are going to design for the ordinate of the reduced spectrum, so elastic spectrum divided by 2.3 or 3.2. And this includes also this nail connection between the angle bracket and the wall, and the nail connection between the hold down and the wall itself. So once we have designed those blue connections as a dissipative, just recall that we need to make sure that the screws and the nails are perpendicular to the shear plane, and that we have a failure mode characterized by 1 or 2 plastic hinges to make them connections as a dissipative. So once we have designed those connections as a dissipative, then we have to design the rest of the structure. And the idea is that all the rest of the structure shall be designed for the overstrength of those connections, which means basically, for example, these joints between panels, between the panels forming the floor, shall be designed for the overstrength of the other using an overstrength factor of 1.3. Also, the joints between the panels and the wall underneath shall be designed for the overstrength using an overstrength factor of 1.3 of the dissipative zone. And also the corner joints, or let's say the vertical joints on the corner between the walls, also this one shall be designed using capacity-based design. If we have a wall with a big opening like this, so when it comes to check the level of strength here, again, we need to use the overstrength factor. So we need to use capacity design to find out from the equilibrium, from the strength of this connection here, the value of the force that we have in this corner. And again, when it comes to designing, for example, the hold down, you can see here a kind of failure mode that was unexpected. So this is a kind of, the idea was that this one should have been plasticizing. Instead, we got the plasticization of the steel bar, the steel plate, meaning that this hold down was either too slender in terms of steel, or there were too many holes on the strap, on the panel. So that's why what I want to say before, according to the new Eurocode A, we will require basically to check, to apply capacity-based design also at the connection level. So here you have a 4 example of brittle failure modes that should have not occurred. Why did they occur? Because basically the idea was very often when you find off-the-shelf those hold down, they were not correctly designed. They were initially designed just for strength and stiffness, but not for ductility. So again, you see, for example, here, we have a withdrawal of screws, of nails, rather than plasticization of nail here. Also here, failure in the plate rather than plasticization, same thing here. Here, failure also in the wood. So the idea is that those connectors should be designed using capacity-based design. So starting basically by designing this blue connection as a ductile. How can we design this connection as a ductile? Well, we can use, like we said before, we can use Johansen equation, this one. And we can make sure that the failure mode will be those characterized by this formula here. Basically, using this relationship here above. So once we have made sure that the ductile connection is basically characterized by flexural yielding of the fastener, then we need to design the rest of the system. So, for example, we need to design the withdrawal strength of this screw here, or we need to design the thickness of the plate, or the strength of this anchor here, or the strength of the wood here using capacity-based design, which means that we cannot design those members for the action coming from the elastic spectrum, for the reduced spectrum, but we need to calculate basically the force, FED, by multiplying the actual strength of the nails by the overstrength factor, which is 1.6, and divided by Kdeg, which is 0.8. So basically, the FED, when it comes to designing, for example, the thickness here of the metal plates, the strength that we need to design, that we need to use for this verification is not the strength of the nails, but the strength of the nails multiplied by 2, twice. Which means that, for example, for the hold down, either we need to increase the thickness of the steel, or we need to reduce the number of nails connecting the hold downs with the timber itself. Because basically the idea, the normal idea of the producer is that, okay, I can put many nails, it doesn't matter, you can put how many nails that you want, and this will improve the strength. Which could be true if you are in a seismic design, but in a non-seismic design, but for a seismic design, of course, it's not true. We need to make sure that the weakest link will always be the nail connection between, let's say, the angle bracket or the hold down and the timber itself. Another important thing, we're just, I don't know what time is it, but we are basically towards the end of the presentation. Another important thing we wanted to make sure is to avoid the soft story mechanism. There's another important thing we all know very well from reinforced concrete. We don't want to have a soft story mechanism. A similar thing may occur also for cross-laminated building or for light frame construction. So in some way, we stole this clause from the steel part. And the idea, the concept which is behind this sentence here is basically that when we have a timber building, or in general, we have a building, for example, a timber building, we know we have a kind of distribution like this in terms of seismic demand. So, of course, lower above here, it's higher here, because this is behaving like a cantilever. Now, the important point we wanted to make sure with this relationship above there is that there is a kind of constant ratio between the strain capacity in blue and the strain demand in red. So we want that there is a kind of constant ratio in order to try to promote, if possible, a full plasticization across the whole height of the building. For this reason, we put this clause there. Because the point is that if, for example, we would keep the strain capacity constant along the height, for example, we would use the same number of down, the same number of screws, the same number of angle brackets all around the height, then we would for sure promote a soft story mechanism here. So we will have eventually less energy dissipation. So again, this clause is aimed at avoiding a localized plasticization in the structure itself. Now, just before the conclusion, I told you before about this work example of design of multi-story CLT building. This was a very useful exercise, actually, to try to test the new Eurocode 8. Because there were many different question marks. For example, the value of the overstrain factor. We are talking about, for timber, 1.6 divided by 0.8, which is 2, which is quite a high value. It means that we need to increase our forces by 100%. And we want also to test some other clauses. So for this reason, we developed this work example design of a multi-story CLT building, which was funded by the Italian Civil Protection Department. So it's a seismic design of a multi-story CLT building in a high seismicity area, which is close to L'Aquila. We're talking about a peak ground acceleration 0.35 G, which is not so high compared to Wellington, but not so low compared to other part of Italy. For us, in Italy, 0.35 G is the maximum. In the future, probably will increase, because historically, if you look back, in the last 50 years, the PGI has increased all over the world. It seems that we are having more and more dangerous earthquakes, so it may increase. So anyway, we use a finite element model with flexible connection, and also the response spectrum analysis, which means a linear dynamic analysis. This is the kind of building we are talking about. There is a finite element model that was implemented in SAP 2000 using shell elements. But the most important thing, actually, is that when we model a building like this using a finite element model, it's very important to remember that those shells cannot be glued together. I remember very well at the very beginning, we were revising some work coming also from engineering in Italy, designing with timber. Often they were losing hours and hours to have very refined mesh, but then they were not modeling the connection. So the important point to consider is that it makes no sense to lose hours to have millions of shell elements after we don't model the connection themselves. Now, modeling the connection is fairly complex. Here we provide like a simplified kind of possibility. So for example, the angle brackets, the flexibility of the angle brackets, they are modeled using this kind of diagonals, flexible diagonal, and so on. So we can find more information about this in this paper that is freely available. If you want, you send me an email, I can send you this paper, which is in English. This paper here is in English and Italian, so this is fine, so there's not a problem. However, as I said before, this work example, unfortunately, is in Italian. It's like, I think it's 200 pages, even more, I don't know. So all the verifications are all reported. However, it's freely available. Here you have a link. And then you need to go, everything in Italian, you need to go to this one, which is Chapter 4, Timber Construction, the meaning of this. And then you get a file, a PDF file, which is called Allegato 4, Annex 4, Chapter 4.pdf, which is freely available. Of course, it's in Italian. It's not the best solution for you, but on the other hand, the formulas are international. And now with all this program about artificial intelligence, Google Translate, etc., since this file is not protected, you can select pages by page. You can put your translator. You can get at least the sense of what is written there. if that may be useful. Now I'm going to conclude, definitely. So just to wrap up a little bit, I would say that this timber chapter of the Eurocode 8 is definitely a step forward in the design of timber buildings. We have finally different structural types, so different lateral load resisting systems, all spelled out quite clearly. We have a complete description. We have updated value of the Q factors based also on the results of all the tests that have been done all around the world. I didn't mention at the beginning because I didn't have time, but I would say that in terms of testing, full-scale testing, there have been lots of testing going on actually done, performed on timber structure. All timber building testing on shaking table. So we have a lot of knowledge. I would say, I don't want to say more than what reinforced concrete or steel because it's not true. But on the other hand, we have very updated knowledge that we could basically use to update the value of the Q factor, for example. We have capacity design rules very clear at the global and local level and all the overstrain factors that were missing. And also a new safety formula for design of significant damage. There is also, but I didn't have time to discuss, also an annex regarding the nonlinear static analysis. So we have also some formula in the annex for nonlinear static analysis of timber buildings. In my opinion, it's still too early because the most important difference between timber building, let's say, a reinforced concrete and steel, is for reinforced concrete and steel, we have a clear formula to calculate the ductility of a plastic hinge. When it's for timber, we are not still ready. We are not yet at that point. So we don't have a clear formula to calculate in a rotation what is the actual ductility of the rotation. So in this way, we are still a bit behind, I would say, compared to the other material. Just want to acknowledge that, of course, this is not, I mean, I'm here to present this. I have a privilege to chair this working group, but this work is a result of an interaction with many other people from Italy, from Germany, from other countries. So it's a really joint effort in the end, And I want also to acknowledge the help of Dr. Maurizio Folesa, who did a PhD on this subject here several years ago. He's now a practicing engineer in Italy. And of course, last but not least, Auckland Structural Group, so basically you, and the Timber Design Society that invited me to be here and to present this to you. So that concludes my presentation. I hope we have some time. I hope I'm not too late. I didn't check my time, to be honest. So I hope we still have a bit of minutes to get some questions, if you want, or some comments on what I will be presenting. So thank you very much. I'm expecting some questions, particularly on this